Good afternoon, Miss Jacinto. Hello. I'll wait just a minute or two more because I'm actually on time. All the technology worked today. But we are going to talk about special rights today. Hello, Hayden. All right, so if when you watch this or if you're with us now, just know that I updated last night some information to your Google Classroom just to kind of keep you up to date on what's due, how you can do it, what's required, when it should be turned in, all that good stuff. For some reason, some of you guys were not seeing the no reassignment in your assignment list. However, that should never have prevented you from actually doing the assignment. And once everything appeared to be updated, all of that should be okay. So with that being said, still get in any of your late work, still complete any of your no reassignments. Again, the due date of yesterday is highly suggested. We want to make sure that we're getting things in on a regular basis so it doesn't feel like a lot of work when we let things get kind of pushed off and we procrastinate. So again, the other no reassignments should have been due as of last night at midnight, but we are still able to complete them and get them into me. The program itself will shut down that part in the assignment column on May 10th. However, just make sure up until then you get that finished, and I will put that in the grade book accordingly. So today we are going to start a new topic. We are still going to be working with right triangles just like we did with our altitude on hypotenuse information. You may have also seen that I put on Google Classroom another question that was asked from your no reassignment in the straight in the stream so that you didn't have to search for it. So all of that was there as well to help you. But we're right back to right triangles, and isosceles right triangles are actually going to help us out a lot in that we're going to have two ways to do the problem. One is our old way, and another one is going to be a new way. So the first thing that I want to talk about is going back to our triangle inequality theorem that said opposite the smallest angle should be the shortest side and opposite the largest angle should be the longest side. So right away we know that we have our hypotenuse across from our right angle. However, what we also have to remember is that if the sides are congruent, the angles opposite them are congruent. And we did that with our isosceles triangle chapter. What that also means is if there's 90 degrees here, these two are not only complementary, meaning they also have to add up to 90 degrees, because 90 and 90 is 180. They are congruent complements. And congruent complements will automatically be 45 degrees. So that means this measure is 45 and this measure is 45. And what you will see if you reference your formula sheet that I gave you once upon a time, we also call these right isosceles triangles. We have a tendency to call them 45, 45, 90 right triangles. So right isosceles gets referred to as 45, 45, 90 in a lot of formula sheets, in the textbooks, so keep that in mind. So with that, we are going to look at a couple of examples to get ourselves a pattern. And I figure what better way to bring in examples than to actually do some of the no-read problems that I did last night. I did both the Honors Algebra 2 and the Geometry no reassignments last night, and I think you'll be pleasantly surprised that at least this one should go by pretty quickly. So I'm going to actually use some of those examples as our notes today. So first thing I'm going to do is we're going to draw our triangle, and we're going to put in all of our tick marks. So notice my black marker already ran out, so we're down to navy blue now. And they're going to tell us that the angles are congruent, and I'm going to tell you that this side is 14. Now, the question that they're going to want us to answer is not just to find one side, but we want to actually find the lengths. And as I write, you should be writing as well. And if you are watching this because you're watching it taped, you can always pause and catch up. So we want to find the lengths of the missing sides. Well, most of us would look at this and go, I can't do this. The Pythagorean theorem needs us to have 2 of the 3 sides. Don't forget, because it's isosceles, our 2 congruent angles tells us this is isosceles because it follows our if the base angles are congruent, then the sides are congruent. That theorem, our isosceles triangle theorem. So right away, we're able to determine that those 2 sides are congruent. So right away, if I want to find my missing lengths, I can say the length of AB is also 14. I don't have, notice it's the length, so I don't have the bar over the top. The other thing that I want to make sure of is that I find what the length of AC is. So I can label it X, or I could leave it as AC. But this time what I'm going to do is I'm going to use the Pythagorean theorem. It's something that we're comfortable with. It's something that we know. So 14 squared plus 14 squared equals X squared. And we're going to rely on our Pythagorean theorem like we've done all along. 196 plus 196 equals X squared. And most of us are going to go to our calculator and find out that that is 392. Now, do not do a decimal. We found out the hard way that as many times as we have begged you to use exact value, that we still insisted on decimals and couldn't figure out why we were getting them wrong in no-re. You weren't getting them wrong. You just were typing the answer in incorrectly. If you wrote this out, you can see that 14 squared was 196. There's 2 of them. So what this tells me is this actually breaks down into a perfect square, 196, times 2, which is our prime number. So by simplifying and using our Pythagorean theorem, you can see that you had 2 of the same thing. It was that number times 2. So you end up with 14 radical 2 as our value for X. So excuse me. Sorry, guys. So let's do another one. I can't stop sneezing, sorry. All right, so we are going to look at this one, recognize the same pattern, and do the same process. Let's rely on our Pythagorean theorem to do this. So again, we have our congruent angles, which automatically tells us that our sides are congruent. And so we're going to look at this as our Pythagorean theorem again. And we're going to 3 radical 5 squared. Now notice, I put it in parentheses. Because if you go to your calculator and do this, it has to be in parentheses. Plus, we know this guy has to be 3 radical 5. It's isosceles. They have to be the same. And this time I'm not even going to label that x. I don't want it to get confused with the other x, and I really don't need to bring any other variables in. We're just going to use yz squared. Oop, I forgot the square there. So now we have to bring back a little bit of algebra 1. And this is supposed to tell me that I square the 3 and I square the 5. And then I'm going to do the same thing here. Square the 3 and square the 5. Now, if you forgot that part from algebra 1, don't be afraid to do it in your calculator. Just make sure you do parentheses. So 3 radical 5. Now notice it opened a parenthesis there, so I have to close the one that's around the 5, and then I have to close it again so that it involves that first one. I'm going to square it using our x squared button and push enter, and the number's 45. Now the reason is because 3 squared is 9. The square root of 5 squared just drops. They cancel each other out. And that's where our 45 came from. If you do not put it in parentheses in the calculator, it will not work out the same way. You'll end up, I think, with 15 in most cases. Same thing here. 9 times 5 was 45. So we end up with yz squared is 45 plus 45. Well, 45 plus 45 is 90. And here's where, oops, I don't know why there's a 4. Here's where we have to then simplify. And we have to think, what's the biggest perfect square in 90? So if I took 90, I could go and divide by 2 and divide by 2. But I'm really hoping that we all see the number 9 times 10, that we know our factors well enough to know that that's a perfect square. So when we do take the square root of both sides, we are going to simplify this by 9 times 10. And if I tried to break 10 down any further, 10 is 2 times 5. Well, 2 and 5 are prime numbers, so 10 is going to stay there. So we end up with 3 radical 10 as our answer for YZ. So when we are going to answer this, especially in the no reassignment, not only are we going to be asked to do 3 radical 10, but don't forget that you are going to be asked to also state what that other segment is. Hey, Siona. Hi, Blake. I was on a roll and sneezing, so thank you. All right. So now let's talk about a pattern that we're going to start to see. I'm going to do one more example, and then we're going to talk about this pattern that actually exists. Now, the other nice part about a lot of these questions is not only am I doing many of them for you that are going to appear in your no reassignment, but because it's isosceles, one of the 2 answers are always going to be pretty straightforward. So let's turn this guy around just so that we're looking at it a little bit differently. Make that guy 24, and we are going to have to find NP and MP. Now, here's where we're going to start seeing a pattern come up because it happens every time. And I am going to very quickly bring this guy back. And I want you to remember that we used the number 14 before. And we worked out our Pythagorean theorem, and we saw that it was the same number squared added together. We saw that 196 popped up, and then when we simplified, we could tell that it was 196 times 2, which got us 14 radical 2. Notice this 14. That's what we had up here. And it showed back up down here. So just kind of keep that in mind. And we're going to come back to this one. And if we're going to find the missing lengths, notice the first thing, and I saw Miss Jacinto did bring this up in the chat. She said, make sure you notice I add my tick marks to the diagram. It tremendously helps, especially if we're moving too fast. So I know that these 2 sides have to be congruent, and that does tell me that this other side is 24. And if I stick strictly with the Pythagorean theorem, I'm going to put them over here now for a reason. I know that this is going to turn out to be 24 squared plus 24 squared equals MP squared. So again, it has that same feel like our other example where it was 14 squared plus 14 squared. So you know as well as I do, we're going to end up with the same number, 576 plus 576 added together. And 576 plus 576 is going to be this really ridiculously big number. Now, I purposely made sure that I had these big numbers because it doesn't matter. If you wrote all this out, you already know what hidden perfect square is in there. Because a perfect square is something times itself. Well, that's what 24 squared is. 24 times 24, 576. You see it showing up twice. So just like before, it's going to, when we go to solve, we have to simplify, and we end up with that 576 times 2 under our radical sign. So I'm using all of this to help me see that that 576 is going to show up again, which is, just like before, the 24 shows back up. Every time. Every time, no matter what this number is, this one will always end up being 24 radical 2 every time. So what they did was, because it happens every time and you see it happening in the Pythagorean theorem, and I won't make you go through the proof of it, but it does allow us to have a formula. And the formula then isn't necessary, but it makes it go faster. So with like a lot in math, we have these observations that later it can make it go faster. So let's talk about our formula. Our formula does happen around a right triangle. So it's not like your typical formula. And you'll see that when we do so, it's like we're labeling the sides. And on your OGT formula sheets at the bottom, you're going to see that that's exactly the way that even the state shows it. Everywhere you go, whatever the books are, you're going to see that the formula is written around our triangle. And a lot of times you'll see they're going to use the letter A. It could be M, it could be Z, it could be F. It doesn't matter. But whatever one side is, you know the other side has to be it. It's opposite those congruent angles. So just like you saw in every one of my examples, I put those pink tick marks in. That's because they have to be the same. And we already said every time we did the Pythagorean theorem, what showed up on the other side is a radical 2. So it makes it nice that if we know this pattern, the ratio then that they talk about of the sides notice this is 1 times A, because you don't see the 1, it's invisible. And this is 1 times A. And now this is radical 2 times A, but the way we write variables and radicals, it's kind of backwards. So it's a 1 to 1 to radical 2 ratio. So that means whatever this side is, this side will be identical. That's what 1 to 1 means. And whatever these two sides are, this side would be that radical 2. So we're going to look again. Very similar. They're going to look the same. This time, though, instead of going through the Pythagorean theorem, we're going to do it using this setup. And I'm going to show you how that'll work. So we're going to say, just like before, find the length of the missing sides. And our triangle is going to be our isosceles right triangle. We're going to say that this side is 37. And we're going to label this D, E, F. Now again, here's this big number. And if I did the Pythagorean theorem, I'd have to know or go to my calculator and get 37 and square it. So instead of doing that, I'm going to write out our formula. Our formula says the congruent sides, so these two sides, will get the same variable, A and A. Notice I even used a different color so that I can see the difference in the paper. Opposite the right angle, always the hypotenuse is A radical 2 because it's supposed to be bigger. So first step, I put my formula around my triangle. The second thing that I want to look at is on this side, I have the formula I wrote and a number that they gave me. It's the same side. Both 37 and A describe the side? They are equal. So because they're equal, we're going to go ahead and we're going to say A equals 37. Now, all of this is most likely going to be, all of this is going to end up being in your mind probably most of the time. So please make sure that what you're looking at is I'm doing it for notes. You very well would be doing this in your mind. So this is what happens, which then means I can go back and now say, well, if A is 37, that means this side is 37 because it's also A. And if A is 37, that means I'm going to plug 37 in for A, but I get to keep the radical 2. And what we find out is that pattern that we saw before, which was 24, 24, and 24 radical 2 with our Pythagorean theorem. And over here, 14, 14, and 14 radical 2 showed up. We have the exact same pattern here. 37, 37, and 37 radical 2 showed up here. So when we list our final answer for NORI, they're going to have EF equals, and you will simply do 37. And they're going to have DF equals, and you will put in 37 radical 2. And that's it. So it is supposed to be easier and faster because what I wrote down, all of that's in your head. So let's change the directions just a tad. All right, so this time, it's the same directions, just written a little bit differently. Find x, z, and y, z. And again, the minute we have radicals, we all go nuts. It's still going to be as easy, and I could still do the Pythagorean theorem. I'm going to choose to use our formula instead. So opposite each of our congruent angles should be our congruent sides. And I know instead of A, I could use F's, I could use G's, doesn't matter. I'm going to use G's. G, G, G radical 2. So it's not the letter that matters, it's the ratio, the 1 to radical 2. So, same thing that you already saw. This side has, and I purposely did this way so that we can see. We have our value where we know that G equals radical 7. So that means on this side, we end up with radical 7 as well. But that means that over here, our G radical 2 will now be radical 7 times that radical 2. So this G radical 2, we're now going to plug in radical 7 for G, and we're going to keep that radical 2 that was already there. Since they're both under the square root sign, that means this is going to equal radical 14. So we still have a number, radical 2. The pattern is still there. Radical 7, radical 2. This is simplified appropriately. So when I write my final answer, the sides that they're looking for, x, z, should be radical 14 because we want the simplified answer, not radical 7, radical 2. They're both under the square root sign, so we need to bring them together. And yz is radical 7. All right, one more. Again, I'm using the numbers and triangles right off of the no reassignment, so I'm using the exact same numbers. Actually, 2 more and then we're all done for the day. I'm looking up at all the triangles I drew last night. I don't know why I did that. It should be capital. So VRNT. And we're going to make this guy 13 radical 2. So we want to find TR and VR. So we want to find the legs. Well, again, I'm not going to do the Pythagorean theorem, even though, and actually I am. I'm going to show you because I didn't do an example like this earlier. I'm going to show it both ways. Right now, if I wanted to strictly do this with the Pythagorean theorem, I know these two sides are the same. If they're the same, let's go ahead and name them both A, because we're going to eventually have them both as A anyway here in a minute with our formula. But if I stick with the Pythagorean theorem, I would actually have a squared plus a squared equals, notice the parentheses, 13 radical 2 squared. I have 2 a squares, so anytime you add like terms, that's 2 or 3, but in this case there's 2 of them, 2a squared. And over here, again, I could use my calculator and just do parentheses, where I'd have to take the parenthesis 13, the square root of 2, close the parenthesis, close it again, so that we have enough closed for open. We had 2 open, you gotta have 2 closed, and we're gonna square that. And when we push enter, we end up finding out that this guy is 338. I'm going to divide by 2 now to solve. So we're going to divide this by 2. And when I divide it by 2, we end up with a squared is 169. And when I take the square root, what we should find is that the square root of 169 is 13. Now it is plus or minus 13, but because we're actually talking about a length, that's why it will only be positive. Had I done this using the formula, so had I used our 45, 45, 90 formula, notice what would happen, and I'm going to go ahead and just redraw this for a second. 13 radical 2 over here. And if over here I decided to use our formula A and A radical 2, Notice this time the side with the formula and the value are over here. You can already see what A is because if these are equal, it already has the radical 2's. So the piece that's missing is the 13. It's already telling you what A is. But we were told set them equal to each other. And if I want to get A by itself, we would divide away the radical 2. Well, when we divide away the radical 2, they're going to cancel. And so mathematically, you now see that it's also 13. Now you can observe it and be a lot faster than doing the Pythagorean theorem and not have to go through all this. That's why our 45-45-90 ratio works so much better, because it just cuts back on time. So when we're all done, and whichever way we've chosen now, TR would end up being 13, VR is 13, and we're finished. I could have put 38 radical 2, and both of these guys would be 38. I could put 17 radical 2, and both of these would be 17. So the pattern works in both directions. All right. The last example is directly, I had the example come up twice. I clicked on the same problem 4 times. The same example came up both 2 out of the 4 times. So 50% led me to believe you'll probably see this example too, and we will end with this one. So we have our special right. We can see both these angles are going to be 45. And we want to find AB and BC. Again, I could do the Pythagorean theorem. I know if these 2 angles are congruent, these 2 sides are congruent, and I could say that they're both x. So if I chose to do this by the Pythagorean theorem, I could say that this is x squared plus x squared equals radical 15 squared. 2 of our x squares make this 2x squared. Because a square root and a square are inverse operations, they will cancel each other out. It all disappears. And we're left with 15. I'm going to divide both sides by 2. And now here's the problem using the Pythagorean theorem. We need to be very careful in how we answer this, because if we go to a decimal and do 7.5, taking the square root of a decimal is going to make us think that we get to use a decimal in our answer. If we use a mixed number, we can't do what we're supposed to do, and at the beginning of the year we talked about how to simplify when radicals are in the denominator. So I am going to leave this as x squared equals 15 over 2. And when I take the square root, I'm supposed to remember, again from the beginning of the year, we did a lot of this in the first couple weeks of school, that this is now x squared equals the square root of 15 over the square root of 2. And if we remember, we are not allowed to leave a radical in the denominator of a fraction. No, it is not appropriate for the final answer. we must rationalize. And we did worksheets at the beginning of the year, and we're talking September. And when we rationalize, we want to make that bottom number a perfect square, which means the closest perfect square to 2 is the number 4, because 2 times 2 is 4. So we're going to multiply top and bottom by radical 2 over radical 2. Because any number, notice the 15 over 2, times 1, that's what this is going to reduce to. Radical 2 over radical 2 reduces to 1. So any number times 1 is itself. It just looks different. So this is actually going to multiply together on top. 15 times 2 is 30. And on the bottom is radical 4. Now, please don't reduce, because you're going to get right back to the 15 over 2, and you're going to have to go back and back and back. What this does come out to be, though, is radical 30 over 2. And it actually, if you think about this, the step I should have done, and I'm going to squeeze this in, I'm going to wait on that 30. It's actually radical 15 radical 2 over 2. Because 15 times 2, notice that radical 2. It was at the bottom, got yanked to the top, and 2 simplifies. So it's like that radical kind of disappeared. So it went to the top, and then the radical disappeared. And because the 15 and the 2 can multiply together, that's where that 30 over 2. So our final answer for x is radical 30 over 2. Now that's doing the Pythagorean theorem. And with this rationalizing, it gets to be a bit much. But if I chose to do this with our 45, 45, 90 process, I could say this side was A, this side was A, and this side is A radical 2. So using our 45, 45, 90 process, I can set these two equal to each other right away. A radical 2 would equal radical 15. Again, the side with the formula and the side with the value, they get set equal to each other. So right away, we are at this division. And we're going to divide both sides by radical 2. It's going to cancel here. And we're left with A equals radical 15 over radical 2. Well, we got to rationalize, which means we're going to multiply top and bottom by that radical 2. And we end up with radical 15 times radical 2 over radical 4. So notice that radical 2 got yanked to the top. What's going to end up happening with that square root of 4? It's going to become a 2. So we end up with radical 15 radical 2 over 2. And you're going to hear that if you say it out loud a lot. You're going to hear the number that you saw, radical 2 over 2. So each of our legs now will be that radical 30 over 2. So when I come back over here, I end up with radical 30 over 2, radical 30 over 2. And both legs are simplified to that. Now that is a question that I saw come up You have the option: your faster new formula or the Pythagorean theorem. Do you want to see me do one more question similar to this last one, or do you want to end for the day? It is entirely your choice. I can do another question maybe a little easier than that, but it is up to you. All right. With that, I will load all of these. I am going to do one more, sorry, but by all means, you guys can sign off if you want. All of this will be loaded to Google Classroom. The example that I am going to put on looks similar. I'm going to make this guy 32 though, so notice I'm not even going to put a radical there. And so the last one that I did had a radical. This one, it doesn't. We'll call this X, Y, Z, and we want to find the legs. So instead of saying find X, Y, and find Z, Y, we're going to say find the legs. So we're incorporating some vocabulary. I am not going to do the Pythagorean theorem. I'm going to just do the special right. I know that my special right formula is and A radical 2. I know that since this side has the number from the problem and the formula I wrote, I am going to set them equal to each other. So A radical 2 will equal 32. I know that I'm going to divide away my radical 2 on both sides. And I am left with A equals 32 over radical 2. I cannot leave it that way. So I need to make sure that I rationalize, and the closest perfect square is going to be 4, which ends up being that it's this times itself. So this turns into 32 radical 2 over the square root of 4, which is 32 radical 2 over 2. So notice, some of us, if we see this pattern reoccurring, will be able to jump from this to this, because it will always be that that radical 2 shows up on top. A 2, so just that number inside, shows up on the bottom. The only thing you have to make sure of is that you recognize that you still need to reduce this because it's a fraction and 32 can be divided by 2. So our final answer here for the legs would be that each leg is going to be 16 radical 2. 32 divided by 2. So the pattern is also what can help it go a little bit faster. Please check Google Classroom. You will find that I am updating everything and I am very clear with what I expect. You will find all of today's notes loaded. Everything in NoRe should be adjusted accordingly, and I will be grading whatever was turned into either Google Classroom or my email pretty much tonight and tomorrow. So continue to email me and I will continue to answer and post. I will hang here for another 20 seconds if you have any other questions, comments, or concerns. If not, please make sure you email me all of your questions and I will continue to email you back. If I don't hear anything, have a great afternoon and get outside and enjoy some of the sunshine. It's still a little chilly, but at least there's sunshine.